take a step length, and while choosing this step length, we can go for figuring out that particular alpha for which the minimum most value of the function along this direction occurs. Then that alpha is called as exact line search. However, if we just somehow that we are not much bothered about exact step, because exact step is very not cost effective, because when we go for optimizing a function, I was mentioning, if you go for exact line search, then optimization inside wants more optimization, and therefore obviously the computational cost will be heavier. And then if we somehow, instead of searching for the exact minimizer, somehow if we just find out some inequalities satisfying which our method will satisfy at least two conditions, that the step length is not very small, and also the decrement of the function values in the consecutive steps, they are also not very small, because unless we take care about these 2 points, that the step length is not very small, and also the decrement of the function value, that fxk plus 1 minus fxk, if this is also not very small, then we have global convergence. Today we shall prove it. But how to assure that the choice of alpha k satisfies both the conditions? For this today's lecture, we will describe 4 ancient inexact line search methods. Those are Goldstein Armijo condition. Then we will consider to talk about Armijo backtracking, then weak Wolf condition, and then strong Wolf condition. These 4 particular conditions we shall talk about in this lecture, and then towards the end, with the help of weak Wolf line search, we will try to talk about the global convergence, because with Armijo backtracking or with Armijo Goldstein, they will be similar, and not only similar, commonly in like standard books, these 2 global convergences will be proved. However, when we talk about Wolf line searches, commonly textbook they prefer not to provide this one. However, they provide later on mixing up with the conjugate gradient, because conjugate gradient never works with the Armijo condition, with the Armijo backtracking condition. Although today several bypasses are there, that conjugate gradient plus Armijo conditions, those methods are there today, but earlier without any trick, like you follow the conjugate gradient direction, and then plus you take up step length as the weak Wolf, you take step length as Armijo backtracking Armijo or Armijo Goldstein, then it was not known how to prove the global convergence of the conjugate gradient method. Conjugate gradient method was known not to converge with the Armijo Goldstein or Armijo backtracking condition, and thereby commonly you will find that textbooks, they don't provide for any general descent method its global convergence with this Wolf condition or strong Wolf condition. However, later on with conjugate gradient plus Wolf condition, this convergence analysis will be there. However, we will prove not with respect to the conjugate gradient, but any general descent algorithm, provided the descent direction dk follows a certain condition that we called as gradient related condition. I will mention what is the gradient related condition, and then with the help of that dk satisfies that gradient related condition, any general descent algorithm also will have global convergence if we follow the weak Wolf or strong Wolf condition. So we will prove this fact, that any general descent algorithm, once that descent direction chosen to be gradient related, with the help of the weak Wolf or strong Wolf, the method has global convergence. That we shall prove. Let's start describing these 4 particular ancient inexact line searches. Today we have many more, and most recent one is the Haggardsing method. It appeared in 2006, and that was much typical. By typical, I simply mean here all these conditions that I shall be deriving, they will follow the decency condition. However, Haggardsing condition, they don't follow the decency condition. Several variations are there, and commonly if we are very stringent about, okay, my method should have decency property, sometimes it has lower rate of convergence, it is slow to converge. However, somewhere if we allow to increase or decrease the function haphazardly, not like in a decent manner it should move on. If we allow at certain steps that, okay, it can increase or decrease, then method has faster convergence. That was observed by Hagar and Jane. Anyway, I am not going to talk about Hagar-Jane method. The most ancient 4 methods are as follows. The first inexact line search I will be talking is the Armijo condition. Armijo line search says the following, that it keeps in mind that the function value should degrade not just slightly, sufficient decrease it should have. And how to assure that the function value in the next iterate should have sufficient decrease. Armijo suggested that let us follow the following procedure, that once we are following a line search at a given point xk, then effectively we are trying to figure out a minimum value of the function fxk alpha dk. Sorry, I was considering superscripts as to mention the vectors and subscript for the scalars. So this function along a direction dk obviously is a function of one variable. Let's suppose we are considering the alpha variable is along x-axis, and here goes your function value. Here let's suppose the function phi alpha is equal to this. It has graph somewhat, let's suppose at 0 it has function value fxk, and then let's suppose the graph of the function looks like somewhat like this, and function value at 0 is this much, phi 0 or fxk. What we want is a sufficient decrease of the function value in the next iterate. Next iterate obviously will lie on this particular line because we are moving along the direction dk, and here is a reflection of dk. This is particularly the direction dk. Along the dk, the function f which we are minimizing is reduced to a function of one variable that we have drawn up. But next iterate obviously will lie then along this particular line dk, and therefore on this x-axis the function, the next iterate also will lie. Here the iterate xk is over here, and then xk plus 1 will be somewhere, we do not know where. But here we should choose a particular point such that the function value degrades at substantial decrement of the function value is there. Then what we do? We consider that we consider to alter the here is this particular level of the function value. We wanted to have a sufficient decrease, and then we alter this line slightly a bit, and then this line we draw up, and this line has obviously certain slope, and that slope will lie in between. We choose this line in between the tangent of the graph at this particular point. We feel that if we move along the tangent, then sometimes the step length will be very small, because at this point a certain kind of, if we feel that it is unimodal, or even if not unimodal, there is a common perception that at this particular point, as the function, I am going to minimize the function, there is a chance that the function will degrade sharply at this particular point at which I am at this point, because from here I need to make a movement. So people, they suggested that, okay, don't take the tangent line as your decrement, because if I consider the tangent line, this tangent line will not have any intersection with the graph, fine. And once there is no intersection, and therefore down of this line we do not have any point on the graph. So therefore if I do not have any, if I consider to have the function value below this tangent line, then obviously I don't have any point on the graph, fine. From this perspective as well, consider a line that lies in between this tangent line and the line y is equal to phi 0, and then obviously in between these two lines I have to choose a particular line, and this line What is the slope of this particular line? This particular line has slope, we notice that phi dash 0, and for this line we have slope is equal to 0, and therefore choose some fraction of C1 times some fraction of phi dash 0, where this fraction C1 lies in between 0 and 1, and therefore this is a line that lies in between the tangent line and the line, the function value at the point xk. Fine. So in between these two lines we are choosing a particular line. The closer the value of C1 to 1, if C1 is closer to 1, then obviously this line moves almost coming towards this tangent line. Then if I consider C1 very close to 1, then I am over aggressive, that function value is I want function value as less as possible. However, if I allow a bit more, if C1 tending to 0, then it will be like my step length can be very much high, because I want the point, next iterative point should be such a point for which function value is below this particular line. If I choose a line like this, then I can choose then my step length can also be this particular alpha, and this alpha will be very huge, and therefore a moderate choice of C1 is always suggested, that you consider C1 lies in between 0 and half. And then you choose alpha in such a manner, choose alpha k such that phi alpha k is less than equal to, what is the equation of this line? This line has slope that, and then starting from phi 0 plus C1 alpha phi dash 0. If we follow this alpha, choose alpha k such that this happens to be true, then obviously function has sufficient decrement, and as well if I am considering C1 not to exceed half, then my step length is also not going to be very high. Both the points are taken care of, that the function value decrement is substantial plus the step length is not also very aggressive, and both the points are taken care of by this particular condition. In terms of the function f, this phi is an auxiliary function. In terms of the function f, we notice that this condition precisely says that it is fxk plus alpha k dk less than equal to fxk plus c1 alpha k. What is phi dash 0? If I consider phi dash alpha, by chain rule we can quickly figure out, this is gradient alpha dk transpose dk. So this will be phi dash 0, so that will be gradient f xk transpose dk. Fine. Now how to figure out this particular alpha? It is okay that we are going to choose this alpha, but how to choose such an alpha? Sorry, yes, thank you sir, yes, it is alpha k. Now here, how to choose such an alpha k? It is okay that if I choose an alpha k of this type, then obviously function value is degrading substantial, as well as the step length is not very high. We agree with this one, but how to choose this particular alpha k? It is suggested that this can be done quickly by a backtracking, that you take a substantially larger alpha k, very high value, maybe let's suppose 10, 50 or whatsoever, and then you backtrack that alpha k I want here, what are the alpha k's, what are the range of alpha that satisfies that the function has value below this particular line. Here the region, here you obviously observe that it is from here to this particular region, is not it? These are the alpha values, the range of alpha values which satisfies this inequality, and then here I cut off because of the intersection, this intersection comes over here. And then how to figure out alpha k? It will be as follows, that sometimes we may feel like I will just go from left hand side and then I will reach at over here, but that will obviously say, okay, your alpha k, there is a high chance that your alpha k will be then very small. So it is suggested that you take a larger step, maybe whatsoever value, maybe you can start with 100, substantially larger, and then you backtrack that 100, then multiply by a fraction, maybe let's suppose half, then 50, then 25, then 12.5, and so on. Once obviously you will reach at inside of this one, and that will be not again very close to the value 0. So by backtracking we can figure out a particular alpha that satisfies Armijo rule or Armijo rule, and also alpha k is not very small. So here start with by large enough, I simply mean that, okay, initial alpha k should not, initial alpha k, by large enough I simply mean initial alpha k should not be chosen such that it is automatically satisfied. Like here, if alpha k is chosen very small here, and then that will be automatically satisfying this one, and therefore it suggests that you take large enough, you take large enough in such a manner that the initial choice is not satisfying that inequality, and then start with a large enough alpha k, and then maybe we choose alpha bar and choose a fraction tau, maybe choose 1/3 to half, choose a fraction. It will be simply a fraction, not necessarily in between 1/3 to half. Commonly in practice people choose in between 1/3 to half, but it is just a fraction that you may consider to lessen it by half or 1/3 or 1/4, that does not matter much. Anyway, choose a fraction tau. After these choices, then reduce alpha by tau times alpha until we observe that f of xk plus alpha k dk is less than equal to fxk plus c1 alpha k gradient fxk transpose dk. So this Armijo condition, this condition plus this backtracking rule, these two conditions together, it is called Armijo backtracking rule, and that is our inexact line search method 1. Next we shall consider the inexact line search 2. It was suggested by Goldstein later on. Backtracking was suggested by Armijo, and later on Goldstein came into the picture and he suggested the following. He suggested, you notice that here is an iterative process, that although we may feel what kind of iteration, like it is just multiplication, no much computation is there, but still depending on, if I choose very large value of alpha, quite a bit of amount of time sometimes it may require here to get out from this inequality. and therefore but our major aim was not to solve any not to figure out alpha k with the help of some iteration, and that is how the inexact line search method is. The inexact line search method was trying to figure out some inequalities. Just by satisfying them, I will choose the value of alpha k. However, here you notice that in order to avoid that alpha k is not very small, this backtracking is essential. And then Goldstein suggested, okay, if we are very much fearing about that alpha k can be very small, why don't you consider one more line and then choose your function value larger than that particular line, but below the earlier line, and that will then be sufficient to say that okay, alpha k value is obviously substantially larger, as well as your function value is smaller than a particular level that is at your own ways, fine. But in order to have intersection region between this line, earlier line below which the function value we assess to have, in order to have intersection region of these two lines, that above of this line and below of this line, in order to have an intersection, we need to have then a C2 here, C2 fraction slope of this line. This line should be lying in between this particular line and the tangent line. So you choose C2 times phi dash 0 to be the slope of the line, where the C2 value is bigger than C1. So C1 less than C2 less than 1 bigger than 0. Under this condition if we follow, then obviously the step length is going to be not very small, as well as the function value decrement is substantial. If I quickly graph out and then figure out a region, here goes y is equal to phi 0. It was our tangent line. We wanted function value should be below this line. This line was phi 0 plus C1 alpha phi dash 0, and it should be above this line. This line is phi 0 plus C2 alpha phi dash 0, where we take up C1 C2 less than 1. Some books, although Goldstein suggested to choose C2, some books later on, instead of choosing these two constants, different constants C1 and C2 satisfying this one, people suggest okay, don't consider two constants. You can take here C2 to be 1 minus C and take C lesser than half. When C as it was, C1 lesser than half, and then 1 minus C1 is certainly then, if I consider C2, C1 less than half, then 1 minus C1 is certainly bigger than C1, and then 1 minus C1 that is less than 1, fine. So if we restrict ourselves C1 to be in between 0 and half, that was restriction in Armijo backtracking, in the Armijo rule. So here is a little bit deviation, different books they suggest C1 and not C2 here, 1 minus C1, but in that case you choose C1 in between 0 and half, that restriction should be there. However, in this restriction you don't have C1 in between 0 and half. Any one is fine, but it essentially says that the function value substantially below than this initial function value and above this particular line. This is not for function value. This line is due to give a safeguard that the step length is not very small, fine. And then we notice that above this line and below this line goes here this region, and above this line and here is a particular region, there is a particular region. So here in between, from here to here, this region, and here goes another region. So these two regions are acceptable region acceptable region in the Armijo-Goldstein rule. In the Armijo-Goldstein rule, in terms of inequalities, we have the following formulation, that choose alpha k such that and fine. These two conditions actually alleviate this iterative hidden process to choose the value of alpha k. This iterative process is alleviated just by this inequality, this particular inequality. Fine. Well, so now next, the inexact line search that I shall consider is the weak wolf condition. And this is our inexact line search 3. We notice from this condition in terms of alpha, I did not write. Anyway, if I write in terms of alpha, then we shall see from the Goldstein rule, we notice that this one in terms of phi alpha is this condition, that phi of alpha k obviously here, but I am not writing with the subscript k here. In general, for any alpha here, phi alpha greater than equal to phi 0 plus C2 into phi dash 0. Fine. And so this is our from the Goldstein rule. The Goldstein rule says that phi alpha should be above this line, above this line I1, right? C2 alpha into phi dash 0. And then we notice that this says that phi alpha minus phi 0 divided by alpha is greater than equal to C2 phi dash 0, and by mean value theorem this is phi dash xi for some xi in between 0 and alpha greater than equal to C2 phi dash 0 for some xi in between 0 and alpha. From this rudimentary derivation, Wolf found that if I replace the Goldstein condition, this Goldstein condition simply by phi dash alpha greater than equal to C2 into phi dash 0, If I replace this one, then the conjugate gradient methods global convergence can be proven. Here not exactly xi, but here precisely when we replace this xi simply by alpha and take that as a rule and replace the Goldstein rule by that rule, that phi dash alpha greater than equal to C2 phi dash 0. It has a very nice geometrical essence, I will mention quickly now. So if we replace this condition by phi dash alpha greater than equal to C2 times phi dash 0, then Wolf found that the conjugate gradient method can have global convergence property if alpha k is following the Armijo condition plus this condition phi dash alpha greater than equal to C2 times phi dash 0. This condition he named as curvature condition. Why curvature condition? I will now try to follow that what is the meaning of this inequality, replacing this xi by alpha, and then we shall quickly figure out why it is called the curvature condition. Accordingly, the Weak-Wolf condition is simply replacing the Goldstein rule in the Armijo-Goldstein rule, replace the Goldstein rule by this rule that phi dash alpha greater than equal to C2 times phi dash 0. Weak-Wolf condition is choose alpha k such that you have Armijo condition plus we have phi dash alpha k. Phi dash alpha k will be gradient of f xk plus alpha k dk transpose dk greater than equal to C2 times gradient fxk transpose dk. Fine. Choose alpha k such that this Armijo condition plus this condition satisfies, and this condition is simply phi dash alpha greater than equal to C2 times phi dash 0. What is the meaning of this inequality? This inequality says alpha k, yes. No alpha k, sir. Here am I making? Okay, this alpha k, yes, this alpha k, equivalent of, yes, with alpha k if I write, then alpha k, yes, thank you, sir. Okay, so let us now try to understand what this inequality says. This inequality says the following. Well, C2 phi dash 0, alpha k should be such a point, such a value, slope of the tangent on the graph at that alpha k should be at least C2 times phi dash 0. Fine. C2 times phi dash 0, here is our phi dash 0, then C2 times phi dash 0 is, let's suppose, this much slope, this much slope parallelly is over here, is this slope. Now choose alpha k such that phi dash alpha k, at that point whatsoever alpha we choose, then we figure out the slope, and if that slope is bigger than this particular slope, then that is an acceptable alpha, right? So here let us try to figure out, starting from alpha equal to 0, this alpha equal to 0 slope is not beyond, right? This is the slope, tangent slope is over here, so this line, so not exceeding. Then slowly if we come, so parallel to this line it will be over here. So starting from here, starting from here. Now slope is now slowly increasing, right? So increasing, these are acceptable. Now slowly increasing, and then it comes out with parallel to x-axis over here, and then it takes a turn positive. Positive value is bigger than this is a negative value. Phi dash 0 is negative because decay is a descent direction. So phi dash 0 is negative value, and therefore but at this point you have slope positive. Slope positive means beyond this negative value. So here still it keeps on acceptable alpha. Here also acceptable alpha because positive slope. Now again 0. But here when again we come back, then maybe a slightly few points, but after that it is now coming out to be not beyond this line here, the slope, we notice that not beyond this one, and therefore till this level we have acceptable from this particular point to this particular point. So the second inequality, the Wolff condition, this condition is satisfied by set of all values of alphas starting from here. At this point we have this tangent line parallel to this line, and this line has this slope C2 times phi dash 0, and then we slowly increasing, and then 0, then positive, still going until this point particular. So this is your acceptable region. But this is only for acceptable region for the Wolff condition. This is our Wolff condition, but we have to consider intersection region of the Wolff condition as well as the Armijo condition. Armijo condition, it was this one. Maybe we consider this one, and then intersection was below this region, means starting from 0 to till below this region, means till this part, and then later on you have starting from here to right hand side, but then intersection region will be this much region. So this region is our acceptable region for the weak Wolff condition. Fine. But with this condition we notice that people observed that it is okay that inside this region the minimizer is there, but if I consider to choose C2, if I am not very much careful, then this C2 can be chosen to be very close to 1, and if I choose very close to 1, in that case we notice that phi dash alpha greater than equal to very close to 1. So then it will be simply like phi dash 0 if I consider, and then this region is consisting of substantially larger value of alpha which are not very close to the minimizer, and then not to differ from the minimizer very much, what people suggested that instead of considering this inequality you take a safeguard of the other side also. Instead of considering this one, we take off in order to not to differ away from the minimizer much, in order to not to differ much away from the minimizer, people suggested that don't only consider this one, this is just one-sided inequality, but you consider that absolute value of phi dash alpha k is less than equal to minus C2 times phi dash 0, and minus C2 you may be confused because this is a negative symbol, and this phi dash 0 is negative, and therefore you need to consider when absolute value I am taking, then we need to take off this one. And once we consider this condition instead of this condition, in order to somehow not to differ away from the actual minimizer, here on the right hand side it may be very big away from the minimizer, we want as close as possible to the minimizer just by the inequalities, then this condition has to be taken, and this condition essentially says the following. I will mention what is the geometry of this inequality, and once we consider this inequality instead of this inequality, it is called the strong Wolff condition, not the weak Wolff condition. But this is continued to be called weak Wolff because any descent method has global convergence only with the weak Wolf condition. We don't require this condition. This condition is bit strange, but very strict. Very strict in the sense of both the sides I have to take care. Here just one side you take care, but it says that both the sides you take care. But it is observed that if we consider this inequality every time to choose alpha k, then the method becomes faster, and thus it is called a strong one because of fastness. But with the minimum possible condition, the method has global convergence. That's why it is called the weakest condition, weak Wolf condition for the global convergence of any descent algorithm. I will now consider to mention the geometry of this inequality. What does this inequality says, and accordingly what would be the possible region of alpha k in which this Armijo plus this strong Wolf condition are satisfied. Plus we consider that gradient of f xk plus alpha k dk transpose dk is less than equal to minus c2 times dk. Geometrically, the strong Wolf condition says that it says that the slope at the point alpha k must be in between c2 times phi dash 0 and minus c2 times phi dash 0, right? c2 times phi dash 0 is this slope. Here was c1 times, this one was phi 0 plus c1 times phi dash alpha into phi dash 0, and now c2 times was this one, this slope, and here is then parallel is this slope, and exactly opposite is this one. So here goes your c2 times phi dash 0, this slope is this line, and this line is minus c2 times phi dash 0. This inequality says that the slope must be in between these two lines, right? In between these two lines means the region, the graph should be in between these two cones, right? So accordingly, this entire cone, this particular region, this region and this region, we map over here. So here is parallel line. Starting from this parallel line will touch upon over here, and then this line. So starting from here, because once we move little away, then it will be intersecting. The graph will be in between, in this region. So starting from here, so this starting from here means, I mean, like the graph will now slowly from here slightly after this line, after this particular, slightly after this value, the graph will be in this shaded region. This is your these two lines. Now graph has to be inside of this region or that region, right? So accordingly I keep on moving, and then we see whether the graph lies in between these two lines or not. And once we move away from here, then we notice that no, after this you don't have this, the graph is again not lying in between these two region, this shaded region, right? So from here to this particular region, and this is your acceptable region for this strong wolf condition, this condition. And then below of this region, and here this entire region is below of this region. So this is your acceptable region for this strong wolf condition. And here you notice that earlier, like from minimizer, the points were far off, the weak wolf. If someone, although the Armijo was degrading this level till this part, but still this part you notice that the alpha value is much away from the actual minimizer. However, it is restricting that the step length is not much away from the minimizer, and that was the idea in the strong wolf condition. Now these are the four ancient inexact line search methods. Next I will go with proving that with weak wolf condition we have global convergence for general any decent algorithm. Maybe today we stop or continue? Okay, fine. Yes. Yes. Yeah, local minimizer. No, actually we are not striving for minimizer, and obviously we are happy with even local minimizer, no problem.
Second question is, in all four methods, we are find out
Alpha dash 0? No, phi dash 0. Phi dash 0. Yes.
So what is the computational advantage of this all four method compared to exact line search? We are not only find root of alpha dash 0, phi dash of 0.
Earlier in exact line search we were solving
Phi dash equals 0.
this equation. We needed to solve this equation, right? And to solve this equation we need to proceed with any of the root finding methods, and root finding method is an iterative process, and then it has computational cost is higher. Here is just two inequalities, like just you follow these two inequalities, choose alpha k that satisfies this and this, no iterative process, it is just a direct process, choose alpha k that satisfies both of them. But here to figure out a value alpha that satisfies this one iteratively we have to process, and I do not know in how many steps I will be able to reach at a minimizer. I will be able to reach at a root of this one. But here nothing like that. Here just like you choose alpha k that satisfies these two. No iterative process. It is a direct process. Earlier it was iterative process. Here no iterative process. Here is a direct process. Okay. Any more question? Okay, then in the next lecture I will prove with the weak wolf condition general global convergence analysis for any general descent method, irrespective of the conjugate gradient method. This wolf condition came into existence only for the conjugate gradient method. Conjugate gradient method could not be proven to have global convergence with the help of Armijo backtracking or Armijo Goldstein. And thus this weak wolf condition came into existence, but later it is a proven fact that with the weak wolf any general descent method has global convergence property. That we shall prove on the next day. And all these methods, we notice that once we have armature condition, all of the four has this armature condition, and armature condition ensures sufficient decrease, and not only just decrease, sufficient decrease. And certainly then all these four methods has the decency property, that fxk plus 1 is less than fxk. This property is there, fine. However, as I was mentioning on the last day, there is another rule, that is called diminishing step size rule, in which none of the conditions are bothered about. Just you follow any alpha k that satisfies that it is square summable, alpha k square is less than positive infinity, and summation of alpha k is equal to infinity. Also, although you don't require this, but you require limit of alpha k is equal to 0 plus this condition. These two conditions essentially are sufficient to take, so that with those choice of alpha k, your method will have global convergence irrespective of what descent direction you choose, but provided descent direction has to be gradient related. By gradient related we simply mean it should not be the descent direction should not be perpendicular to the gradient. The descent direction that you choose should not be perpendicular to the very close to the gradient. That is called gradient related. I will mention the mathematical condition. What is this one? So as long as you choose dk this one plus you choose the alpha k, forget about whether decency is happening to be true or not. Obviously, if I choose alpha k deliberately by this rule, this decency will be fail to hold, and therefore without decency even the method will have global convergence. These two properties I shall prove on the next day. O plus any descent method will have global convergence, or alpha k diminishing step size, by this we mean diminishing step size plus any descent method where the descent direction is chosen to be gradient related will have global convergence. Fine? Chalo, thank you.
Is a consequence of the first one. If the series is convergent, then the general term tends to 0.
Okay, yes, you are right.
So this is redundant.
We don't, redundant.
Yeah.
Summation of alpha k
Plus infinity.
It will be plus infinity.
So you need probably a sequence like 1 over k.
1 over k, but even 1 over root k also will work. But yeah, that also has this infinity, right?
Yeah. So this is